The first issue we'll talk about is distributed deadlock detection. So what can go wrong with deadlock detection in a distributed system? Well, imagine here we have our 5 machines, and on those 5 machines there are 5 different waits for graphs. You can see on the leftmost machine T1 is waiting for a lock that T2 has, and T2 is waiting for a lock that T3 has. But there's no cycle on the first machine. On the second machine, T1 is waiting for a lock that T3 has, and T2 is not waiting for anything. On the third machine, T3 is waiting for T2, and that's all. On the fourth machine, T2 is waiting for T3. On the fifth machine, T3 is waiting for T1. So on each individual machine, there is no cycle. But if you look at the colors and letters of these transactions, you can see that there is actually a waits for cycle going on here. And so basically what we want to do is we want to get all of these little local waits for graphs. We want to bring them together in a single place. And when we do that, we'll see the cycles that go on across nodes that involve multiple transactions. So deadlock detection is easily fixed. Periodically, each of the nodes ships its waits for graph to a designated master node. It can be any one of the nodes that's designated as the deadlock master. And at that master, it gathers up the union of all the edges of all the waits for graphs, and it forms a global waits for graph. If the global waits for graph has a cycle, that means that transactions are waiting for each other in a cycle and there's a deadlock. And then in the usual manner, you can abort one of those transactions to break the cycle.